Welcome to a new lecture in the series of lectures on single agent search. This lecture doesn't fit into the original series, but new research is always being done on this topic, and I'm teaching this class again in winter of 2023. And so I thought I would record a new lecture talking about a new algorithm related to bi-objective search. So that's something we haven't talked about before, and I thought would be a nice addition to the course. And also working on a demo. At the time of this recording, the demo isn't on the web page yet, but I expect it'll be there soon. So let's start to talk about bi-objective search or multi-objective search. So multi-objective is the more general case, and we're also going to be thinking about bi-objective search. And so what is this problem? And this is actually something that comes up quite often in different domains. And the idea is that we might have multiple measures in a problem that we want to optimize. So for instance, if you are thinking about planning on a map, we might want to minimize the time, but we also might want to minimize the distance that it takes. And sometimes the route, which is the shortest distance, actually takes quite a bit longer, but sometimes the route that it takes the least amount of time could actually be going a farther distance. The shortest time could actually be going a longer distance. And so we might have some trade-off that we prefer between minimizing the time and minimizing the distance. If we're playing a game, so you could imagine just a game scenario where I have some agent here. So let's draw a picture over here. I've got some agent here, and the agent is thinking about, it wants to go somewhere through the world, and it might have several routes that it could go. And you could imagine here that there's going to be some like enemy turret that's sitting right here, and maybe there's another path that could also be taken, but that path would be requiring it to go quite a long distance around to the goal that it wants to go to here. And so you could imagine, I have some trade-off, like if I go through this path right here, then along this portion in a game, you may say I'm going to take some damage, so maybe I don't want to do that. And then, of course, if I choose to go around in the other direction, I come around this way, I can totally avoid the damage, but that I would get over here, but I'm going to go a much longer distance, and it'll take me longer to get there. So strategically, that may not be something that I want to do. So that's a trade-off that I have. And in any given scenario, what we might choose is you could statically combine some set of metrics, right? So I could say I want a path that minimizes, I'm going to weight somehow the distance and the damage, or the distance and the time. Or if we think about elevation, a path, I want to minimize the change in elevation, but I also want the shortest path distance. So we could think about this as well. So any of these we could choose statically to say, I'm going to have, some C1 times measure 1. And then plus, if I'm only going to do two objectives, then I'd have 1 minus C1 times measure 2. And then I could just write that down. And if I write down a single C1, then it would tell me exactly how I want to trade those off. And I can just use A star like I'd normally use. But maybe I don't know this ahead of time. So I don't know what this should be. I don't know what the right thing is. And what I actually want to do is present to some user or some other decision agent a set of all the possible ways that this could be satisfied. And if we say, if we present all the different ways, then the person or the agent or whatever it is going to be able to trade off or make that decision when they're actually looking at this problem. They may have some other information that we're not aware of or other things like that. So that's what the multi-objective or bi-objective problem is looking at, is this question of when I have multiple objectives, bi-objective being when I have two, how do I trade them off? And what we're going to be doing is not just looking for one path that is a reasonable path that trades them off in some maybe reasonable way, but we're going to think about finding all paths that are non-dominated, and I'll define that in just a second. Okay, so given as input, what is my input going to be? So my input is going to be a cost function. or I can have a number of cost functions like C1, C2. There could be more. If there's only two, it'd be bi-objective. If there's k of them, then we're going to be multi-objective. And this is going to be for a graph. We'll call it a graph. Of course, the graph could be implicit, or they could be other things like this. But a graph is going to have vertices and edges, but the cost of the edges is different for each of the different functions we're using. Okay, so as input, I'm going to get these cost functions. I'm going to get a graph. Now the question is, do I get as input for one of these problems a heuristic? The interesting thing is that I might be provided a heuristic, but in order to solve this for all possible values of C here, what it means is that I'm going to have to solve it for C1 equals 1 and C1, in this case, being 0. So basically, I have to solve the measure 1 exactly. I'm going to have to solve measure 2 exactly. And so it's very much the case that we could just make it part of the algorithm, that the first thing you would do is you would solve each of these problems exactly for each of these individual measures and then build a perfect heuristic. And this is likely to pay off in practice because there's an exponential number of paths in general. And so if we can, if we're going beyond where we need to go, searching states that like a more accurate heuristic would allow us to prune, when we're thinking about at least individual measure here, then it may be worthwhile to just compute the perfect heuristic ahead of time. And in some sense, we're going to have to do that search anyway. Okay, so we've got this cost function, or set of cost functions, one or more, two of them being bi-objective. We have a graph, and now we're going to search it. So what do we need to find? We want to find all. So let's write what the output is going to be all, and that's the key here, non-dominated paths. Okay, and so of course then we immediately have to ask the question, what does it mean for paths to dominate each other? And if we're going to look at this, then I'm going to imagine that I have two paths. Path 1 is going to be P, and P is going to have cost P1 and P2 according to my cost function. In this case, it's a bi-objective cost function. And then I'm going to have Q is equal to Q1 and Q2. Okay, so two paths, they have different costs. Again, this is the cost under the first cost function, and this is the cost under the second cost function. And so we want to say, what does it mean to dominate a path? So we say path P dominates Q. And we can write this as P and this sort of curly less than sign here, which I can't draw so well, but it dominates Q if and only if we have the following conditions. So one is that if P1 is less than P2, and then fix that up here, not P. Sorry, this is P1 is less than Q1. So what we're saying is the first measure here has to be less than the second measure, so strictly less, not less than or equal to. If the first one is strictly less, then P2 can be less than or equal to Q2. Okay. Or, so this is my first condition, or P1 is equal to Q1. Okay, and this is basically the less than or equal to here. We're going to get this on the other side, but we already know we have the less than, so this is the equal to side. And here we have, and P2 is strictly less than Q2. Okay, so these two pieces together tell us what it means for one path to dominate another path. So this is a strong domination. If we had less than or equal to on both of these, this would be weak domination. And so it says that, look, at least in one metric, then P in one of the cost metrics is going to be strictly better than Q. Okay, so I can't always be the same, but like in some way I'm going to be strictly better. I have a shorter distance, even though I don't have it maybe a strictly shorter. Maybe we have the same time, but I have a shorter distance. Okay. And once we have a notion of a domination relation, so we want all non-dominated paths, we want to actually say what is the frontier of solutions. So all non-dominated paths is actually what's called a Pareto optimal frontier. Okay, and here I'm going to give a definition for this. So given a problem, we're going to think about what does it mean to be a Pareto optimal solution. So given a problem, and I'm going to change my notation here slightly, but so I'm problem, I'm going to use a capital P for some problem. This is a bi-objective or a multi-objective problem, P, and then we're going to ask what does it mean for something to be non-dominated or to be Pareto optimal solution. So given instance P, a Pareto optimal solution which we'll call pi here. So this will be one answer for P. Is a solution such that there does not exist pi prime such that pi prime dominates, that's my curly domination, dominates pi. Okay, so we're thinking about a Pareto optimal solution is one that is not dominated by any other solution. And so we can, for what we're going to think about is for all other solutions, is there another solution that dominates pi? Then this would not be on the Pareto optimal frontier. And the set of all solutions, so the frontier, the Pareto optimal frontier, is all Pareto optimal solutions. Now, just to make sure that we understand this, we need to make a distinction here. Thinking about this, like maybe, hopefully, what I've said here so far is making sense. But there's some things here that are a little bit different in the way that we think about bi-objective problems. That's quite a bit different than the way we think about regular search problems that A* would normally be solving. And so, in particular, we might think about, so we can think about some problem here. So I can imagine I have a problem. And I could go here, and I could go here, and I get to this particular state right here, which is the same state of the state space. So if this is a grid, we could think about this being, 0, 0, and this is 1, 1, and I can go two different paths. Maybe I can't go diagonally, but I can get to from location 0, 0 to 1, 1. So in the actual state space, here we are, we're going to reach the exact same state twice here. But the costs here, so we can imagine that in one of these, maybe it's very fast, but I go a long distance. And the other one, I go a short distance, but it's going to take me longer. Okay. And then at the end of that, so, this isn't necessarily on a grid, because on a grid we'd have uniform distances, but we're representing it here. So I might have a short path, and I might have a fast path. And therefore, when I reach this state here, so I come along either path, I'm going to have these two choices. And normally in A*, we would say, well, I'm just going to choose what's shortest here. But we can't do that anymore, because now what's happening is that there is no, neither of these paths is strictly better than the other. Neither of them dominates each other. Because at the end, you might say, well, I want to see both possibilities, and I'm going to choose some trade-off in the end, or some other agent is going to choose some trade-off between distance and time. And so we need to keep track of both of these, because we're going to return all of them. Again, that was a problem definition, return all non-dominated paths. Okay, so when we have something like this, we're going to come to the exact same state here. And so a state in our search, we don't any longer want to think about the state being just like an XY location or something else in the world. A state we really need to be thinking about is the path that we use to get there, in particular the cost of the path to get there. So every state in my search, or a node in my search, is actually going to represent this state and the path that was used to get here. And so when I come back to this state, I can reach it. In fact, you could have many, many more paths here. I could reach this state many different ways. And as long as each of the paths is not dominated by one of the previous paths, then here I'm going to be keeping track of many, many different paths to the exact same state. And so let's just look at a picture here. So I'm going to go over on this side. And we're going to look at a picture of what the Pareto optimal frontier looks like. And here, here we're going to think about this as a bi-objective problem, just because this is a lot easier to write out than it is for a multi-objective problem. But we're going to imagine here that we have some cost function C1, some cost function C2. And what I'm going to do is I'm going to draw here I'm going to draw a single state in many different ways. So you could imagine I have a single state that I can reach, and we could imagine what are all the different paths by which I could reach a single state. Now, in practice, these might actually be much closer to each other, but this is going to be good enough for our purposes here. Okay, and so what we're going to think about is the Pareto frontier. When we think about this picture, the picture is actually very helpful. So again, now this, if I think about a search to a particular goal, we can think about all of these are the goal state in the original state space. However, in my search, there are going to be different nodes in the search because all of these have been reached by different combinations of cost for C1 and C2. And so I want to ask which ones are dominated or not dominated by other ones. And so the domination relationship is telling us, basically, I want to look and say, is there going to be something here, looking at this relationship here, P1 less than Q1, P2 less than or equal to Q2. Now, none of these we could imagine, there's maybe no ties here as I think about all of these. So we're going to look and say, really, P1 and P2, if I have a point where the two coordinates are less than the other two coordinates, then we're going to have this domination relation. So I'm just going to choose an arbitrary point here. We could imagine drawing this here. And what we're going to say here is there a domination relationship? Well, this point dominates this point up here. The reason being is that in C1, it has a lesser value for C1, and it has a lesser value for C2. So when I do this, we can go up into here and we could say, well, everything that is in this part of the space up here is dominated by this point, which is on the corner here. And this one, they're tied perhaps. Okay, so we can decide that they're tied, in which case this point would still be dominated by this because in one metric it's less. So in C1, this point has a lesser value of C1. In C2, they have the same value. But that's still good enough. Okay, so up here, these are all dominated. And I could do this. There's a number of different ways I can do this, but it actually should be fairly easy to see here then what are the points that are not dominated. And so I'll draw these in green. So if we think about this point here, there's nothing below and to the left of it. So this is going to dominate everything up here. This point is going to dominate everything up here. This point is dominating everything up there. This point is dominating everything up there. And this point is dominating everything there. So what we have is we have a frontier that is coming across here. And of course, there may not be points in between there that we can reach, but what we're able to say is that everything in this area up here is dominated, so all those points. And the frontier of non-dominated points are these ones right here. Okay, so essentially, if there's nothing below and to the left of you, then you are non-dominated. So there's an interpretation here, so a geometric interpretation of where we sit geometrically. The points up here all have a point that is below and to the left of them. And what we're trying to do is we're trying to find this frontier of that trade off the C1 and C2 in the best way possible. Okay. Now, this frontier does not have to be concave or convex. It could point either direction. In either case, the points would not be dominating each other. So we can see that in this portion here, and we can see that in that portion there. Okay, So again, a little bit funny here, but what we're going to do is we're going to be searching to the goal state, the exact same goal state for all of these points. But what we want to do is we want to find the sets of costs for C1 and C2 on each of the paths such that those sets of costs are minimal. And it's useful here if we're going to start thinking about algorithms to think about what are the states that are necessarily expanded. So if we think about necessary, we'll go back to black here. If we think about necessary expansions, just very informally here, we can have something very analogous to A star. So an A star, a necessary expansion is going to have anything with F less than C star. We have to expand anything that could, that if we didn't expand it, we might miss a shorter path to the goal. And so here, now, of course, we have these many non-dominated or dominated points, and perhaps some that are non-dominated, some that are dominated. And so here, what we're thinking about is we need to expand any path that could lead to a non-dominated path. And so, in the middle of the search, I'm not going to know this, but when I think about all my potential goal states, then if I have a path that is not dominated, so I could have a path here, in the middle of my search, I have some path that's led me here, and that path, in the end, may actually end up getting me to a goal that's over here. But this path, if it's sort of sitting with some set of costs for C1 and C2, especially when you think about F costs, then this path right here is potentially dominated, it's potentially dominating of this path. And so we have to expand the path right now. It'd be necessary to expand that. Okay, so we need to expand in general, we need to expand any state, actually we'll say any node that is not dominated by a goal. Or sorry, by another, well, okay, so we're going to say not dominated by a state or a node on the Pareto frontier. Okay, so there could be, as I said, going back to this picture, there could be some node here in my search that right now is not dominated by something on the frontier, and so we may have to expand that. We'll have to expand that to ensure that it doesn't lead to a better goal state that would then be on the Pareto frontier itself, or it might even be here where it's not dominating anything, but it's not dominated by something else as well. Okay, so what I'm going to do here is we're going to think about if we were just to be running bi-objective Dijkstra search in a naive way, and we're not going to necessarily even be writing down full pseudocode for this. And once we've talked through sort of what Dijkstra algorithm has to do and what the cost of it is, then we'll look at an algorithm called BOA star, which is bi-objective A star. And we'll look at why bi-objective A star is able to search efficiently. And so if we just think about Dijkstra's algorithm, because it ends up here that the heuristics are not doing anything that's very complicated. Most of the work is coming from the fact that we're having to do this bi-objective search. So if we think about bi-objective Dijkstra, and there is an algorithm that describes this. This is there's a 2019 paper by Sedona, Noda, and Colebrook that comes from the operations research community that's thinking about how to do a bi-objective Dijkstra. And but I'm not going to use their pseudocode or anything like that. It's very different than what we've been doing in the course so far. So if we think about just Dijkstra, then what do I have? I don't have heuristics, but I have just G1 and G2. And so what I'm going to be thinking about is the nodes in my search. And as I think about the nodes in my search, then I'm going to be actually what I was exactly showing in this picture here. So I'm going to be doing some sort of search. I'm going to come to a node in my search, which has a particular state, but also has a G cost associated with it. What is the G cost that we reach there? And we have a sense here that we need to expand anything that's not dominated. So we're going to be basically generating nodes and doing dominance checks. And what we're going to look at is why sort of a naive bijective Dijkstra will be very expensive. Now I have here we're going to do, we'll think of it as bijectively. In this case, there's going to be no advantage to bijective or multi-objective, but we're trying to understand here sort of what do the algorithms have to do and why are they expensive, or why is this a little bit complicated? And again, this is going to be is caught up in this example here. So we can basically, if we think about my search now, with my two cost functions here, I can be searching through these in any order. And so if we think about going through sort of in this way, where we're going to think about minimizing C1 plus C2, that means we're going to be sort of sweeping our way through the space this way. In this line would be the priority, C1 plus C2, and we can just sweep through here in this order. And then as we establish this line, we'll know that everything above it has been dominated, and we'll just push this line until it goes as far as it needs to go, until we've reached everything that is non-dominated, and then there'll be nothing left to expand after that. Okay, so this could be written as a general best first search, and we could just expand by min G1 plus G2, coming from our two cost functions. In general, it would just be, we could do the sum of all my different G costs coming from my different cost functions if we're doing multi-objective search. Okay, so we just do this ordering, which corresponds to this sort of diagonal sweeping through the state space, thinking about G1 and G2. And what's going to happen now? Well, when I come to a node, as I'm thinking about G1 to G2, I'm going to come to some node in the search. We'll just continue to use example. So I come here, minimum G1 plus G2, I get to some node here. And what do I have? Well, so I get to some state, but we have a node in the search. And so just to be concrete, let's just say here, I'll write some numbers down. So let's say along the first path here, we reach this node, and in our first cost metric, we had a cost of 3, and the second cost metric, we had a cost of 4. And then we can imagine that we did another path here. So these could be done in any order. And here we had another path which is cost 4 and cost 3. And we can see that neither of these paths dominates each other, right? So in this case, in the first metric, P1 is less than Q1, but P2 is not less than Q2. And that works both ways around. So neither of these dominate each other. So both of these are potentially part of the Pareto optimal frontier. And there's, of course, going to be some paths continuing from here, although these could also be the goal. So as I continue to come here, I'm going to continue to find costs that are going to be a variety of costs for each of my different objectives. And at this particular state in the state space, I could have many, many, many different nodes, every node of which has a different cost. And so here, I'm going to choose to expand the state that has minimum G1 plus G2. But as I expand that state, what I need to do, or as I generate states, I generate a state of new node. Normally what I do, so right, I generate my successors, and I'm going to look at my successors and say, have they been explored already? And what I have to ask is at some node, so for successors, I need to check if they are dominated. Okay, that is, I need to check to see, is there another path that already exists that's better? Okay, and this step right here actually is a really important step in a general bijective search or multi-objective search. This is actually the most expensive step. Okay, because in general, we can actually have an exponential number of paths that get to any node here, any state in the state space. So we get an exponential number of nodes that represent all the paths. And if none of them are dominating each other, so we just have these slight variance in costs, then sitting here, we have many, many, many different costs. And I have to check against all of them to see if they're dominated. And this is actually the major expense of bi-objective search, is as we search, the graph itself that we're searching may not be very large, but we get this blow up in the number of paths that are coming from the nodes in our search. So states could be small, the nodes would be much larger. And so this is really expensive to do this in the worst case. And so the reason in this lecture I'm choosing to actually present bi-objective A star is because it offers a way around this. So that's sort of a novel idea that is worth talking about and presenting here. So if we're going to get to bi-objective A star, we need to first think about what's a lexicographical ordering. Okay, and lexicographical ordering really is just a sorted ordering. What does it mean to sort? And we can have so when we think about ranking and unranking functions for building heuristics, which is going to happens in another lecture, we can talk about that. If we're generating states, we want to generate states for a combinatorial problem in some sort of sorted order. But here we're going to think about a lexicographical ordering. So we just imagine that I have some cost. Now we're going to move to F cost. So we have some F1 and F2 for two states. Then the lexicographical ordering says order F1 low to high, and then order F2 low to high. Okay, so just to make a quick example to show how this works in practice, we'll do an example here. So I might have a set of states 3, 4, 3, 8. So I've already put these in lexicographical order, but 4, 6, 4, 10, and then maybe 5, 4, and 5, 7. And we could continue here. So this set of states is in lexicographical ordering. Just move them up a little bit. And why are they? Because here where this first metric is going sorted from low to high, 3, then 4, then 5. And then among these that are tied, then these are going to go from low to high, from low to high, and from low to high. Okay, so that's lexicographical ordering. Again, we can do this for any number of cost functions. We just sort the first metric, and then a secondary sort on the second metric, and then a third tertiary sort on the third metric, and continuing. Okay, and so there's a general algorithm called NAMOA star, N-A-M-O-A star, that was from 2010 that allows you to do bi-objective search or multi-objective search, and it is able to solve this problem, but the problem is actually a little bit expensive because of the cost of doing the bi-objective checks. And in general, you really can't avoid when you have sets of states here that may not dominate each other, then you can't avoid the checks that happen there. You just have to check, what if we're looking for all the states on the frontier, and there's many of them that are non-dominated, we have to find them all. But what we're going to look at is BOA star, and so BOA star is, we'll go on to the next page here, and get this back to black. So BOA star is an algorithm which is bi-objective A star. And bi-objective A star is actually a relatively new algorithm. As I said, this is from 2020. Oops. 2020 by Carlos Hernandez-Oloa and his colleagues. And what this algorithm is going to do, again, which I think is quite interesting, is that it's going to take advantage of lexicographical ordering to simplify the A star search in a bi-objective problem, but this is only going to work for a bi-objective problem to improve the dominance checks. So basically it's going to avoid having to do multiple dominance checks that might occur at a node here, and that gives a nice speed up in practice. Okay, so we'll talk about how we do this. So what is going to be a node in the search? So a state is just a state in the state space, but a node is going to contain the state. It's going to contain G1, the G cost, that we reached under the first cost metric, G2, the cost under the second metric. Here we could keep H1 and then compute F1 from it. So we'll just say F1 and F2. So these are, these are just path costs. These are estimates on the total path cost. And then we're also going to keep the parent. Okay. So the nodes in here are a little bit expensive. There's a lot of information we have to keep here. But in addition to this, actually, let's just move this out of the way. Put this over here. In addition to this, what it's going to maintain, so inside the search, like something on the best, when we're doing the best first search, what is a node in the search? It's going to be all of this information. We're also going to contain per state. And this is important. So this is per state versus this is a node. We're going to keep the minimum. So this is called G2 min, using the notation here, of a particular state. And G2 min is the shortest path that was found in the second cost. So this is the G2 here. We're going to keep track of what's the minimum we've seen there. Initially, that's infinite. And so so just to give you a high-level view of what's going on, and then we'll look at the pseudocode. We'll think about what's going on here. So what's going to happen basically is it's first going to search in G1, and it's going to find the shortest G1 cost. In fact, let me go back to this picture here. So we talked about if we were just to use G1 plus G2, then this is equivalent to sweeping across the state space this way. And as we do that, then, we just see many different nodes here. And if we see many different nodes here, we're going to see them with different costs. And there's going to be, different dominance checks and things like that have to be done. But what's going to happen is that BOA star is going to order these in a particular order. So what it's going to do actually is it's going to order them in this way. So it's going to start with the lowest C1. It's going to go from the lowest to the highest C1, and correspondingly, it's going to go from the highest C2 down to the lowest C2. So we're going to keep track of the best cost we've seen for the C2 metric, and then we're going to have that decrease. And essentially what it's going to do is it's going to guarantee that we come across the frontier in this direction. And by tracing across the frontier in this direction, what we're going to see is that C2 is always going to decrease. So the G cost of, remember that these are all the same state. They've just been reached by different costs. So as we reach it, the G2 cost has to always be decreasing, and the C1 cost is always going to be increasing as we go across here. And so that's how it's going to order its search. And because we know that G2 is always decreasing, we can use that as a pruning mechanism. And we're actually, because we sweep across this way, we know that we're going downward this way. And then we only have to check basically the last state on the frontier. So if I know here that C1 is always increasing, and this is the last state, then if I reach another state here and I've decreased my G2 cost, then I know it's part of the frontier. So what it's going to avoid, like I don't actually have to check against all states that I've reached previously, but I only have to check against the previous state because I've ordered them in this way. If I'm coming across diagonally, then I could find these states, like I could find this one and then this one and then this one, and there's no guarantee of what happens to C2. But by searching across this way, then I get this property that this is monotonically decreasing, and actually C1 is going to be monotonically increasing. Okay, that's the high level of what's going on. Let's just talk about the pseudocode, and then we will wrap up. Okay, so what do we do? So the algorithm is looks fairly similar to a best first search. So we're going to put start on open. And again, when we put it onto open, this is going to be one of these nodes here. So we're going to have the cost so far is 0. We're just going to have our H cost from this state to the goal, and no parent, and the state is the start state. And there might be a step before here, which is to compute the perfect heuristics, but we won't show that here. Okay. And then what do we choose? How do we choose? So our loop here is while open is not empty. And normally we terminated our search, like in an A star, as soon as you find the goal, you terminate. But in a bi-objective search or a multi-objective search, we have to find all the goals, or all the different nodes that reach the goal, all different paths. So we're actually going to exhaustively search until open is empty, and then we're going to be done. And what we're going to choose to expand is find the lexigraphically smallest node on open. And we'll just call this, we'll call it X. Okay. So in general, then this is the state with the lowest F cost. If there's a tie between F cost and, lowest F cost in the first measure, and if there's a tie between the first measure, then we'll choose the lowest F cost in the second measure. Now there's going to be a dominance check here, but I'm going to skip it for just a second. So there's going to be a line here we'll come back to, because we're going to look at the overall structure, and then we'll come back and say what is the pruning. Okay, so if S of X, so this is the state that is the state part of X. So when we say S of X, this is just referring to the state here. If S of X is the goal, then we know it's non-dominated, so we're going to add this to the goals. So we found another non-dominated solution. And else, what we're going to do is we are going to expand this state. So we're going to say for all successors y of X, then in general what we want to do is we want to add y to open. And all I've done here is I've just skipped some lines here. There's a check we're going to do here, and there's two checks that we're going to do here that allow us to do our pruning, our dominance checks. Okay, but if we look at this here, right, while open not empty, we find the best node to expand. If it's the goal, then normally we'd terminate, but we want all goals, so we're going to just add it to the list of goals. And then for all successors, every successor y of X, then we generally want to add y to the open. But we need some more efficiency here, so what we're going to add is a couple things. So one, what we want to do is we want to check if a state is dominated. So I've reached this state that is associated with X. X is a node, and we're going to ask, is there, for this state, like, is this dominated? And it could be dominated in two ways, because now we're thinking about F cost. So the first way that could be dominated is if G2 of X is greater than or equal to G2 min. So if I reached it by a more expensive path than the minimum that I reached before, then I'm going to say, hey, I know that I'm not making my way down the frontier. So just to say, coming back up here. So I've reached this, there's some state here, but I reached it at a higher C2 cost. Like previously I reached it here, and now I reached it again, and the C2 cost is higher. Then it actually means it's dominated by whatever node I reached there before. Okay, so if G2 of that state is greater than G2 min of that state, here I've written X, it's actually the state inside X. So I could write S of X there. Then I'm dominated. The other way I could be dominated is there could be a goal somewhere that's dominated. And so this would be if F2 of X is greater than or equal to G2 min of the goal. Okay. So if I think about the F cost of this state, I've reached it so far, and then I think about the heuristic that says that's the lowest cost that I could reach the goal. And so if at this point I'm guaranteed that I'm going to reach the goal with higher cost, according to the best cost I've seen so far in G2, then I can go ahead and prune it. And so what we're going to do here is just need to move this over a tiny bit. So do that. Then here it's just really a continue statement. This state has been pruned, and we're going to go find the next state on open. The second thing that we're going to do is, since we're not dominated here, and only after I check that I'm not dominated, now I can say that G2 min of x is going to be assigned G2 of x. Okay. And I've abused my notation. So here I said S of x is the state associated with it. When I've said x in all these places, really I should be saying this is all meant to be accessing. Well, here I'm accessing the path cost associated with it. I have to be looking up. I'm looking up some things here, like here of this G2 min of the state here. So this should be the state, and this should be the state associated with x. Okay, but that's fairly minor. And then, so this is actually good enough here, because this just means that I'm going to check every node right here, and if it's dominated, then I'm going to continue, and then I'm going to update my G2 min. But here, I'm actually generating all successors, and as I do this, if I've generated a successor and it's already dominated, then there's no point in generating it again. So we can do basically exactly the same check that we did before, but we can just do it here to avoid adding it to the open. So what we're going to say is if G2 of y is greater than or equal to G2 min of y, or S of y here, then it's dominated, or it's already dominated at the point that I generated it, so we don't want to generate it. Or if F2 of y is greater than or equal to G min G2 min of the goal. So exact same logic here as up above. And this is just serving to, this line here is just serving to do initial pruning, so I don't have to add so many states to the open list if I don't want to. Okay, so this is BOA star, bi-objective A star, and what it's doing is it's using this lexicographical ordering to improve the speed of search. And here, so lexicographical ordering just says, look, we know that our G2s have to be decreasing. And because we're doing this in the lexicographical smallest ordering, that means my F1s are, we're going to go find the goal with some F cost F1, which is going to be essentially the minimum cost that I can get here. Now I have to be a little bit careful, because we're going to find the minimum C1, and there could actually be multiple C2s here. So at the same time, actually, we're going to find both the minimum C1, but also the minimum C2 that corresponds to that. If there's multiple possibilities, we're only going to find the minimum. Okay, so we're going to find that minimum there, and when we do that, then it's going to guarantee then that as we continue our search, that C1 is the C1 cost of our paths is going to be increasing, the C2 is going to be decreasing, and so we've already found the minimum. So this is always going to be going up, and we're always, because we're doing a lexicographical ordering, we're always going to see these states go up. And then we use this G2 min. We use it, well, we're going to update it here, but we're using this G2 min in three ways. We're looking at this particular state, and we're looking at relative to the goal, and using it to say, hey, if we're not continuing to reduce the cost, because we found the most expensive G2 cost first, so if we're not continuing to decrease the cost, then we can prune these out. And by doing this, there's no, even though there may be hundreds of possible paths that go through, possible nodes then, each node corresponding to a path that goes through a particular state, we don't actually have to compare all of these in practice. In practice, the only thing we're doing is comparing to the single value of G2 min. And so that's what's really powerful about this algorithm, is that reduction to only storing G2 min. So this is BOA star. I would look, let me write down the rest of the reference here. So this, as I said, was a 2022 paper, or sorry, 2020 paper by Ulloa, and Carlos Hernandez Ulloa, and a number of other authors were on that paper, but he's the first author. So if you look at that paper, the one thing I would recommend is if you want to understand this better, you'll find the pseudocode here. But they also find some examples in that paper. And this lecture is already getting long enough, so I'm not going to go through any examples in detail, but you'll find examples that you can walk through to understand it better. And as I said, in the near future, I'll be putting up a demo that will show BOA star running in practice. So I hope you enjoyed this bonus lecture on a new topic of recent research. And there'll be some other new lectures that will be added in the future as well. So thank you for coming, and hope you enjoy all of this.